goods and makeup air solutions. We'll go ahead and start recording this webinar for those of you who might not be able to join today but would like to join later. My name is Mike Moore. I work for Newport Partners, which is a building consulting firm specializing in residential construction. I'm an engineer with a specialization in building codes and standards, especially as related to mechanical ventilation and makeup air. And I serve on the ASHRAE 62.2 committee and have for the past several years. Brian Wellnitz is also online. Brian is a marketing manager for kitchen ventilation for Brown, Newtone, and Best products. And he'll be standing by to answer any manufacturer-related questions that you might have regarding products. That can happen at the end of the session. Today's webinar is going to be about 50 minutes in duration, 45 or 50 minutes, with 10 minutes or so available at the end to answer any questions that you might have. So please feel free to enter those real time in the toolbar that you can see there on your screen. Let's see, we've got a lot of ground to cover, so we'll go ahead and just jump right into this at this point. As an overview for what you can expect to learn today, we're going to be covering the following topics on the subject of makeup air for domestic kitchen range hoods. First off, what it is and why it's needed, kind of the background section there. What are the model code requirements in the International Residential Code and International Mechanical Code? We'll hone in on some of those and kind of expand on them. We're going to look at gravity dampers versus motorized dampers and what the code has to say about that and some practical considerations as well. We'll look at common configurations for installation and typical options that are available to installers. And then we'll also cover a live demo of a design tool that's been developed by Brown and Best to help designers and builders demonstrate code compliance, and also for code officials to review the design and verify that the design at least is in compliance with the code. This webinar is going to be eligible for AIA and VPI credits, so if you're interested in those, please see the slide at the end of the presentation for how to qualify. As I mentioned, we'll also have questions and answers. The questions you can enter throughout the presentation, and the answers we'll address at the end. So before we get going too far in this, we'd like to get some feedback for just helping us understand a little bit more about who you are. And if you would, please go ahead and just enter this for us, and we can figure out how valuable this is to you guys in different industry fields and run some analytics, hopefully, to figure out if we're hitting the needs of a different population. We've got a lot of different people who were invited to participate in this webinar, and we're hoping this reaches a lot of your different questions on the subject. So it looks like most of you have voted right now. Just give it a couple more seconds. About 80% are ringing in. And it looks like we've got architects or engineers at about 20%, about 12% builders or remodelers, 10% code officials, about the same amount of contractors, and a large percent of you consider yourselves as other. So thanks for doing that. We'll go ahead and close the poll at this time. So what is makeup air exactly? I'm guessing you have some understanding of that if you're on the call today and you have some kind of interest. But based on paraphrased definitions of the 2015 International Mechanical Code, which has the most comprehensive definitions out of any of the model codes, makeup air is considered outdoor air and transfer air used to replace exhaust air, which kind of leads us to the next question: what is outdoor air? And outdoor air is air that's designed specifically to enter the building through a ventilation system, through intentional openings, or by infiltration. So outdoor air, you see, can be intentional or unintentional in its entry into the building. So when we talk about how it flows into the building, again, there are intentional openings that we have, such as a makeup air damper that was designed specifically for this application. that could be integrated with the range hood. And then you have cracks and gaps that exist around doors and windows and other openings in the building where you can have air enter from the outdoors based on pressure differentials across the building envelope. Here's a schematic of what you might see from a design perspective as far as where makeup air comes from. That's a question we often hear. And of course, the blue arrows here will represent the outdoor air, so you can see cracks and gaps around doors and windows, and also an intentional makeup air opening, in this case located in the kitchen. And transfer air, meaning that air can enter from other spaces in the house that communicate freely with the kitchen range hood and flow into that area based on pressure differentials and natural movement of air. I also have combustion air called out here with this black arrow directly into the mechanical room, and just wanted to point out that that's definitely different than makeup air, and want to keep those separate in general to ensure that the mechanical equipment has sufficient makeup air for its, combustion air for its needs. So another poll for just a second here is, why provide makeup air? And I'd like to see some feedback from you on this and what you think as an audience. We'll provide some more information on this in just a second, but just before we really get into it, just wondering what everyone out there thinks are the reasons to provide makeup air. Is it to promote good indoor air quality, to avoid excessive depressurization, comply with code? The code officials will probably be jumping on that, or all of the above. And what I'm getting from a lot of people is all of the above, and if you said that, then you would be correct. Provide makeup air. You've got to meet code requirements. If you're a builder or contractor, you're acutely aware of that. It's important to minimize the chance as well of excessive depressurization, which if unchecked could lead to backdrafting of combustion appliances, extinguishing of pilot lights that might exist on old combustion appliances. Underperformance of range hoods would be another problem that could result from depressurization if makeup air isn't provided in a sufficient quantity. Exhaust and sewer gas reentrainment is another one as well. So basically, we want to provide makeup air to ensure that combustion appliances and exhausts are in a good position to operate as designed, assuming, of course, that they're installed correctly. So unless the building's exhaust and supply flows are perfectly balanced at all times, some level of depressurization is likely to occur when the exhaust appliance operates. So what we're trying to do here is not eliminate depressurization entirely, but to keep it at an acceptable level. So based on examples, or I should say based on recommendations from the Building Performance Institute, the maximum depressurization that's acceptable can be determined as a function of the type of combustion appliance. And the most common metric used to measure depressurization is the Pascal. So for those of you who aren't familiar with Pascals, 25 Pascals is equal to 1/10 of an inch of water column. So that just kind of gives you the conversion there. For natural draft appliances, what you're seeing here on the left, a maximum depressurization of 5 Pascals is recommended. When we're dealing with mechanical draft appliances, and you see this fan assist here on the water heater, showing that it's a mechanical draft, a maximum depressurization of 15 Pascals is recommended. And for direct vent or sealed combustion appliances, a maximum depressurization of 50 Pascals is recommended. So 5, 15, and 50 are kind of the numbers I want you to keep in your head as we're going through this for new construction where these appliances are individually vented. So let's get then into makeup air code requirements. Within this webinar, we'll focus on the code requirements of the 2009 and 2012 versions of the International Residential Code, which is the most widely adopted model code in the nation. You can see here on this map where it has been adopted statewide. California, Minnesota, and Wisconsin have state-specific makeup air requirements that we're not going to address today, but these other states have very similar requirements. And the IRC and IMC, International Residential Code and International Mechanical Code, requirements for domestic kitchen range hood makeup air are virtually identical and include three basic components. First off, it's when to provide it, and that's when the kitchen exhaust rate exceeds 400 CFM. They say how much to provide within the requirements as well, and that's makeup air that's approximately equal to the exhaust. And then what you're supposed to include here, as far as a hardware perspective goes, is a means of closure automatically controlled to start and operate simultaneously with the exhaust system. So that's what we're looking for here, and all of these requirements can be met by specifying a motorized damper. You're seeing a picture of Brone solution over here in the right-hand corner that's sized to provide the required amount of makeup air when open during operation of the range hood. So if the makeup air damper is properly sized, the solution doesn't have to be a fan-powered solution. It can just be a passive solution that automatically operates simultaneously with the exhaust system. So let's talk about gravity dampers for a second. One question that we hear from some professionals is, can I use a gravity damper to comply with the code? And in short, the answer is no for several reasons. First off, they're not approved by code because they can't be automatically controlled to open with the operation of the range hood. Secondly, they're generally not listed and labeled, so it's hard to tell what pressure differentials they'll operate at. We reviewed about 30 products from 7 manufacturers that are available through the nation's largest HVAC distributor's website of gravity dampers, and of these, only 7 products were provided with data on the pressure differential at which the damper would begin to open. And of these, the average pressure differential required to operate them was 17 pascals, which is over 3 times the recommended depressurization limit for natural draft combustion appliances. So just not a good solution from that perspective. And finally, industry sources like ACA Manual D and BPI note that properly vented combustion equipment can backdraft at very small pressure differentials, like 5 pascals or less, such as we just mentioned. So backdrafting can be a byproduct of specifying gravity dampers where you're not sure which pressure differential they'll actually operate at. Here's a picture of a gravity damper that came from a real install back in 2000. And you can see the canvas hinge here with some rivets. And basically, gravity dampers can come in all shapes and all sizes and all varieties. So you really can't have a guarantee on that the gravity damper is actually going to open when it's needed. So many of you are aware that while today's webinar focuses on the current regulations, we know that the codes are always changing through public proposals, which are not always for the better. And despite the reasons that we gave to disapprove gravity dampers for range hood makeup air, there is a proposal to approve gravity dampers that's advanced past the first round of the 2015 IRC code development process. So if you're a code official, you can vote to disapprove gravity dampers at the public comment hearings next week in New Jersey. So for the 10% of you out there that might be headed to New Jersey next week, we just ask that you consider that when you're at the hearings. So let's take a break from the regulations for a second here and look at, in the case that if you don't have local code that requires makeup air, what are the manufacturer recommendations for makeup air? So Brone, Newtone, and Best recommend makeup air when any of these situations occurs, when, say, the exhaust capacity of the range hood exceeds 300 CFM, if the home is considered to be of tight construction or well air sealed, then that would be another reason to provide makeup air. Or if the dwelling has natural draft space heating or water heating appliances that are located indoors, that's of course another reason to provide for makeup air. So let's get into some installation configurations here, and just some typical installation configurations that are permitted by code and that are options for installers. The first installation option that we'll look at here is interlocking the central fan with the operation of the kitchen range hood and the makeup air damper. If those three are coordinated through a system of relays and controls such that when the hood turns on, the makeup air damper opens and the central fan turns on, and the makeup air duct is ducted to the return trunk of the central air handler, then you have a few advantages here. You can increase the flow capacity of the makeup air damper by increasing the pressure differential over that outdoor air duct, so you're actually pulling in more outdoor air with the assist of that fan. You can also promote mixing of the makeup air, so there's a bit of tempering before it reaches its final destination in the kitchen, and provide for a little bit more comfort for the occupants potentially, depending on the severity of the climate. A second installation option would be to just duct the makeup air damper into the return trunk of the central duct system, but not interlock the operation of the central fan. So a little less complicated than the first installation, a little less costly, but you have less tempering at this point than you would before as far as running the air over the heat exchanger. But you do have some mixing going on of the air before it reaches its final destination in the kitchen. A disadvantage is that less flow is provided because you don't have that central air handler to provide that boost that's necessary. The third installation option that we have is routing the makeup air damper to the interior register, and not integrating it with the duct system at all. This is the simplest code compliant option, but it doesn't have the advantages of tempering or mixing. If you're using this option, Broan recommends that you don't dump the makeup air right on top of the range hood, because that could result in short cycling of the exhaust air instead of exhausting the actual air that you want. So just a brief overview here of the three different options that we identified and the advantages of each. You can see that that central fan integrated solution provides the most advantages, but all these solutions can be used for code compliance. Another thing to think about when installing the solution is the outdoor air intake and where that's going to be. These are just common requirements within the code that address issues such as screening, clearance, and also location of the makeup air that's being introduced. So don't forget about those code requirements when you're specifying the system. So a little more involved here for you architects and engineers that are in the call. We're going to address some makeup air theory and building science consideration, which hopefully is a little bit of interest to the others of you on the call as well. So when you're talking about a makeup air solution, we've seen that the code has some very basic requirements for makeup air, but we've also covered several considerations that should be taken into account in designing a makeup air solution, such as the type of combustion appliance and its ability to resist negative effects of depressurization. Is it natural draft, mechanical draft, or is it direct vent? Another question is the air tightness of the dwelling. How much infiltration is available for makeup air, and how much needs to be provided through dedicated openings through the building envelope? What about the installation configurations and the boost that you could get through integrating this with the furnace? And the actual kitchen exhaust flow as opposed to the nameplate rating. The fan may be rated, let's say, at 1,000 CFM, but once you get the ducting in and all the elbows, you might not be providing that total flow. So the governing equations that are out there that were used in developing this tool can get a little complicated and a little involved. So for the time being, we're just going to leave the theory to Darcy, Weisbach, Holland, and Nashray. And all you have to know is that the Broan makeup air tool uses these equations so that you don't have to. However, if you're an architect or engineer and want to actually size these ducts on your own, you can reference ASHRAE fundamentals and they have a lot of great equations that can be leveraged. But just know that the basis for this tool is grounded in engineering design. So let's look a little bit more here at Broan and Best Makeup Air Specifier tool, which is a proprietary tool for Broan and Best and Newtone products, but can also be leveraged for other kitchen range hoods as well that come from other manufacturers for code compliance. And I'll get into that a little bit later here. One of the most difficult parts of complying with the makeup air requirements of the IRC is sizing the makeup air intakes, and then of course demonstrating to code officials how the design makeup air flow is approximately equal to the exhaust flow. So Broan, Newtone, and Best have developed a freely available online tool to help building professionals with this step. The tool is going to overlay the engineering equations that we saw earlier with user-specified design criteria, and a state-level code adoptions database is integrated as well. And with all this overlay and this engineering design, we can develop specific code compliance solutions with rich outputs and documentation. So again, all these considerations go into the tool. So right now we're going to go ahead and step out of the presentation for a second, and we're going to then step into the Makeup Air tool. So you should be able to see now Broan's homepage on your screen. And from this homepage, you can select on the top toolbar here, Specifier Tools. So I'll go ahead and select that. And on the left-hand side here, you see Makeup Air tool is an option. There are a couple other tools that Broan has as well for code compliance of mechanical ventilation systems. This is called the Range Hood Makeup Air Specifier, and you see a lot of legalese and introductory text here about the different systems and just a background on the tool, kind of a primer on what it's supposed to do. But we'll skip that for now and just go ahead and select the state that we want to design in. I'm selecting New Jersey in this case because that's where the code hearings are in another couple weeks. So we'll try to get a solution that's directly applicable for New Jersey. As you go through this tool, you'll see these eye icons, and these are informational icons that you can select to get more information on the specific input to figure out what exactly the tool is asking for here. So the county is selected. You can see all these are the counties that are in New Jersey, and these will repopulate when you select your particular state of interest. The county is used not to determine the specific code requirements, which are linked instead to the state level within this tool, but the county is selected to get feedback on climatic considerations. So we'll just stick with Atlantic County right now. The next input is the range hood nominal rated flow, or basically the nameplate rating of the range hood. Most people are going to know the flow, and you can go ahead and drop down and select a specific flow from this drop-down box. If you don't know the flow, but you know the range hood model, then all the Broan, Best, and Newtone range hood models are populated here in this drop-down. As soon as you select a specific flow, then this drop-down will repopulate and give you the relevant models within the Broan, Newtone, and Best line. So let's just go ahead and select one of these models. You can see as I'm doing this, this design exhaust rate bar is updating the whole time. And I've selected a 600 CFM model, but the design exhaust rate is 390 CFM. So you might wonder, well, how is a 600 CFM range hood only exhausting at 390? And that's basically because of the default exhaust duct dimensions and layout that are given here. If we go ahead and provide more realistic exhaust duct dimensions that might be used by a contractor when it's installed, you can see that the design exhaust rate is recalculated here in the tool based on the specific fan curve of the model being selected. So if we want to maximize the flow rate, I've gone ahead and selected 10 as the 10 inches is the exhaust duct diameter. And you can see that we're up to 580 CFM based on this length and number of elbows. You can, of course, change this, and as you change the length and number of elbows, you can see that the exhaust rate is going to fall with more elbows and more length. So there's another input here called additional exhaust rate, if any, and I'll just click on the information button here. And this basically says that, that if you want to consider other exhausts that you're expecting to operate simultaneously with the range hood, then you can account for that within the design. This is not required by code, but it's just an option for the designer if they want to do a more conservative makeup air sizing here. We'll leave it at 0 for the time being and just assume that we want to do minimum code compliance. And so we have our design exhaust rate at 570. The next step is, or one step I guess I skipped over here, is this question of interlocking the makeup air with the central air handler. So if you remember before, the design installation configurations that we had before, actually the 3 of those that are available, one of which has the option to interlock the makeup air with the central air handler. So you can select yes or no. Right now it's selected as yes to maximize the flow to the makeup air damper. Let's go ahead and select no and see what happens. And we see that we're getting this error that says for the tool to work properly, you need to select a non-zero design depressurization level or select yes to interlock the makeup air with a central air handler. So basically this is just saying you either have to say that I'm okay with this building being depressurized and passively bringing in air, or I'm going to actively interlock this, this design with the makeup air handler. You got to get the air in somehow is basically what this is telling you. So let's go ahead and select a non-zero design depressurization level. And if you recall before, we had the 5, 15, and 50 as the 3 major choices. And let's assume that we've got a naturally vented water heater. So in this case, we'll select 5. And if you don't recall the guidance provided before, you can hit this information icon and see that these are the BPI recommended depressurization limits based on the type of combustion appliance. So that resource is always available for you. Next, we want to enter the square footage. Let's say it's a standard new construction, about 2,500 square feet. The average ceiling height, about 9 feet. And these inputs matter because they're going to tell us how much infiltration is going to be available through building leakage. So a measure of infiltration is the ACH 50, the air changes per hour at 50 pascals. And you can get this number through a blower door test, or if you don't have it, you can make a conservative estimate. I'm going to choose 3 ACH 50 in this case for just assuming it's an energy efficient, tightly built home that's compliant with the latest 2012 energy code. So we'll go ahead and select 3. And then we have to know what are the characteristics of the outdoor air duct. Are we using flex duct? Are you using smooth metal duct? And that's going to make a difference on the resistance to airflow through there and how much air you can actually expect to get. So again, a lot of engineering calculations that go into this tool. We try to keep the inputs as simple as possible. Seems like a lot the first time through. Once you go through this a couple times, it becomes pretty routine. Combustion air openings are another thing to consider. When you're doing a blower door test in compliance with industry guidelines, you leave the combustion air openings open. So any air that's flowing through that this tool is counting for, we need to subtract the combustion air opening contribution to that flow to ensure that we're not counting combustion air for our makeup air. So if we've got a naturally vented water heater, I'm going to say we've got maybe 50 square inches of open area for combustion air. So let's go ahead and take a look at our solution again. We've got a 600 CFM range hood, or our inputs, I should say. This exhausting about 570 CFM. is what we're expecting based on field conditions. We're saying that we'll let the building depressurize to 5 pascals, and we've got our parameters entered to figure out the infiltration contribution. We got our combustion air openings entered as well. So now we'll hit find makeup air solution. And as you can see here, this is not going to be a palatable solution for most builders out there or contractors if you're looking at 5 8-inch dampers to provide the makeup air required. The good thing about this tool is that you don't have to stick with this number. You can go back and change your inputs to come up with a more acceptable solution. So based on our tools that we have here, one of the biggest changes that we can make is to, first off, interlock the makeup air with the central air handler. Let's go ahead and say yes to that. And if we're going to interlock it, we know that we can get more flow through. And so we need to estimate the available static pressure down here at the intersection of the outdoor air duct, or the makeup air duct, and the return trunk. Basically, how much suction do we have when the fan's operating that we can rely on to provide this makeup air? So let's say we have about 0.15 inches water gauge, or 37 pascals, available to pull that air through. If we keep everything else the same and then we hit find makeup air solution, you can see that we're down to 2 makeup air dampers that would be required for this solution. And those would be 2 8-inch dampers. If you're thinking that that's still not acceptable and you want to get down to 1 damper, well, you can look at other options as well. Like, what about the design depressurization? 5 pascals is pretty conservative. And if you have if you go ahead and change out your appliances, say this is a new build and you're considering all your design up front, and you say, hey, I could go ahead and put in mechanical draft water heater and a mechanical draft furnace or direct vent. Always select the design depressurization limit of your weakest link for your water heater or your space heater. And in this case, let's say we increase it to 15 pascals because we're going to specify mechanical draft. We find the solution again, and we're down to 2 6-inch. So that's better than 2 8-inch, save a little bit of money there. And if you wanted to, you could play around with these parameters some more and get to maybe 1 8-inch damper or 1 6-inch damper. So you have a lot of different options there. You can also downsize the exhaust ducts and decrease the design exhaust rate, but at that point you're kind of defeating the purpose of the kitchen range hood. We're assuming that the range hood is sized based on the range's needs. So let's go ahead and take a look at this design solution, and assuming that we're okay with the solution as a designer, then we can look at the output information here. So you get a product listing of the dampers and the wall caps that are recommended for use with this particular solution. You got the product numbers there so that you can make out a cut list and order the parts. And then, of course, you can use other dampers or other ranges as well. And let me touch on that for a second before we go on. So if you're using a range hood that's not a Brown or Best or Newtone solution, what you want to pay attention to is the design exhaust rate. And what you can do is mess around with these parameters, input parameters here, until your design exhaust rate is matching the criteria of, that you're looking for your particular fan. So if you're looking for a bigger fan, then you just change the nominal flow and change the duct sizing until this rate matches your expectations for your solution, and then you can apply this recommended solution to your particular application, even though this tool is made for Brown, Best, and Newtone products specifically. So let's go down here and look at the makeup air solution. You can see there's very specific information about New Jersey and the code that has been adopted there as a statewide minimum code. Also recommendations to check with your local jurisdiction in the case that they've adopted a more stringent code than the statewide code adoption. There's information for the code official about the tool and the equations that are used, the background for it, as well as the size and number of the makeup air dampers, and that they're meant to be in compliance with specific sections of the code, so they can see that the thought was given to that. We've got a section in here that addresses considerations for climate zone as well. And again, when you selected the county previously, it maps to the climate zone. And in this case, there's a mixed humid climate zone. So you might think about considerations as a designer as related to summer conditions. If the range hood is going to be used a lot, if you have a heavy user or expect a heavy user in this house, if it's a custom build and you know the user, then you might consider supplementary dehumidification or operation of the AC unit with coordinating that with the operation of the kitchen range hood and makeup air. And if you're ducting into a fossil fuel fired furnace, then preheating the outdoor air may be necessary depending on the volume of makeup air that's being introduced. In a lot of cases, you can actually get away without having to do this, preheating that air, and the IRC specifically permits introduction of outdoor air into the return plenum. You do need to make sure that manufacturer's requirements, however, are satisfied. So when we're looking at the printout here, the output, we've got all the design details that were given by the user. The project name and location are actually entered into a user interface that I skipped just in the interest of time today, but you'll see that the first time that you use this tool, that'll come up. If you use it multiple times in one session, then you won't have to keep entering this information. But that's basically just to provide detailed information for the printout for the code official to demonstrate compliance. You'll notice a lot of the inputs here that were given, and you'll notice some outputs as well, such as outputs that answer the questions of how much of the makeup airflow rate is supposed to be provided through the outdoor air ducts based on the solution, and in our case it's 310 CFM. And you can see that building leakage should contribute for 260 CFM at the design depressurization limit that was selected by the user, in this case 15 pascals. So very detailed information to show how much infiltration is assumed, how much of the makeup air comes through the makeup air duct, even the assumptions related to the available static pressure and return trunk, the duct roughness, etc. So rich information here for the code official to verify that a thorough design has been conducted. There's this print option here as well, and this will take you to a PDF that you can go ahead and then print out and present to the code official. And it's just 2 pages here, so fairly concise with a lot of great information there. So at this point, we've gone through an example of the operation of the tool, and just want to take a break for a second here and get another poll underway to figure out how helpful this was for you. So let me see if I can show this. So we'd like to figure out, based on who you are and what situation or where you come from, how helpful this webinar was for you, and we'll be able to run the analytics later on to be able to figure that out. It looks like we got about 50% response so far, and about 50% of you are saying that it's very helpful. Got about 10% extremely helpful, and about 30% are coming back with moderately helpful, and at least 1% of you, this is complete review and it's not at all helpful. So you must be very familiar with all this process. So I'll go ahead and close this out at this point. It looks like I've heard from about 85% of you. Thanks for that. And at this point, we're going to open the question and answer section and address some of these questions that you guys had throughout this presentation. It looks like there are quite a few of these that have been input, and we won't get to all of them today necessarily, but we will answer them all individually. So after this webinar, so rest assured that we will respond to you later on. And so it looks like we have at least one question that's oriented to a manufacturer, it's specific to a manufacturer. So I'll go ahead and let Brian Wellnitz field that at this time. Brian, would you like to hop on and address that one?
Sure. I think the question refers to, I think it was variable makeup air damper, and would we consider or have we considered designing something that would work in conjunction with a multi-speed range hood. The idea being that when you have a multi-speed range hood, you don't necessarily need to have makeup air at low speeds, only at potentially at the high speeds or the mid speed. The answer to that question is we actually considered this, and what we've found is that given the duration of time that a range hood is typically operating, that the added expense of having what I would call a multi-tiered operational makeup air damper wasn't very cost effective. The reality is that range hoods are only turned on for a very, very small percentage of time, and the overall effect in terms of energy savings, because that's really the only thing we're going to accomplish, it would be minimal by having what I would call a variable makeup air damper. So I hope that answers the question.
Great, thanks, Brian. We've got another question here from Steve that says, let's see, can any of this be applied to other exhaust ventilation applications, such as providing makeup air for bathroom ventilation fans? This tool's been specifically designed for makeup air for kitchen range hoods. You can, based on the inputs that were there with the tool, let me see if I can go back there for a second, you can select the additional exhaust rate, if any, and compensate for, let's say, bathroom exhaust fans that might be operating simultaneous to the operation of the kitchen range hood that are expected to operate at that point. But for now, it doesn't size makeup air for bath exhaust fans in particular. Just fans that might be operating at the same time as the kitchen range hood, based on the designer's desire there. So at this point, the tool doesn't have that that option. Let's go on to another one here. We got a comment that it would be worth noting that the BPI standard is actually even lower, -2 and -3 pascals for orphan water heaters and commonly vented furnaces and water heaters. That's a very excellent point. And if we go back to the tool here, you can see that, let me click on this design depressurization limit button, and you can see that that information is contained in here. Orphan water heaters at 2 Pascal and natural draft, commonly vented with water heaters at 3 Pascals. So excellent point. We were focused mostly on new construction today, but those are things to definitely be aware of in doing an existing construction retrofit. Let's see some other questions here. I've got another comment here. In terms of related makeup air factors to consider in the home, it would be helpful to address 2 other items. 1, identifying any competing exhaust devices in the home, and 2, practical considerations for tight homes with open fireplaces. Number 1, again, could be addressed through this additional exhaust option that's available within the tool. But yes, that's another great suggestion. Practical considerations for tight homes with open fireplaces. If they're open, then depressurization can result in entrainment of either combustion products or just particulate matter that's in the flue. So those are considerations that the designer should take into account when selecting the acceptable design depressurization limit. Got a question from Paul Raymer here. How does the exterior hood or termination fitting work into the design exhaust rate? And the way that the tool is set up is that it assumes a constant value for the equivalent length for the end cap. So we had to make a call here on how many inputs to have and what assumptions to make. And while there is definitely a difference in the performance of the exhaust caps and the flow that's let through, we decided to go with just a standard assumption there. So there is a standard assumption for that that's integrated into the tool that's basically hardwired. Got a question from Alan saying, how does the tool interact with HRV and ERV systems? And the answer is that HRV and ERV systems are typically considered balanced systems. So they should be able to provide the exhaust and supply streams that they're rated for. I won't say regardless of the depressurization of the home, but they have their own fans that can regulate that. Obviously, the higher the depressurization of the home, the harder the HRV or ERV is going to have to work to overcome any resistance created from that on the exhaust side. On the supply side, they might actually receive a boost for that side if depressurization is helping to draw more air from the outside. So we don't have, the tool doesn't specifically say, hey, you should tweak your HRV or ERV this way. I would assume that that it would have some impact, but we haven't quantified that at this point. Okay, let's see. Why explain how to tweak the makeup air damper tool to produce the answer 1? And does this not send the wrong message? A question from Debbie. And maybe tweak is the wrong word to use there. What we're really trying to do is not tweak the tool necessarily, but to change the design. We have to understand that as homes get more complicated, there are a lot of design options that users have and that HVAC contractors and builders have. And when you're talking about tighter homes, options for combustion appliances and associated acceptable depressurizations, as well as ducting length, location of equipment, location of intakes and outlets. You can pull a lot of different levers in there and produce an intelligent design that will satisfy code requirements and also provide the necessary makeup air to ensure that we don't have excessive depressurization. So that's a better way to look at this, is how do we optimize the design, keep it cost effective, and ensure that we're meeting code and building science objectives. Let's see, we've got another comment here from Debbie that hot, humid climates would need to be ducted to return air to dehumidify makeup air entering house, as demonstrated by Joe Stiebert's ventilation strategy. So that's another good point that we did bring up in the considerations of the tool, that the manufacturers generally recommend integrating the system with the central air handler to provide some sort of tempering as necessary, and also to improve the flow through the ducts. So in a hot, humid climate, you would have the benefit of dehumidification through passing that hot, humid air over the coil before introducing it into the house. Of course, the coil may or may not be functional depending on if there's a call or not for cooling. So you could obviously go to a larger effort there and integrate the solution with automatic operation of the AC system if you wanted to, based on outdoor conditions. The solution can be as complicated as you want it to be, but again, it can be as simple as you want it to be too, and minimally code compliant. Got another question here from Steve, saying, what is the minimum flow rate of kitchen exhaust fan for which the software tool and the makeup air damper solution is relevant? So code says that the minimum kitchen exhaust rate, or the minimum kitchen exhaust rate to trigger a makeup air requirement is in excess of 400 CFM. For this tool, we're looking at the design exhaust rate in recommending compliance. So, so if you select, for example, a 300 CFM range hood, but then you have an additional exhaust rate of over 100 CFM, then this tool is going to recommend a solution for you, and you can go ahead and play around with different inputs and see what the recommendations are in your state. And sometimes the tool will say, if you don't have a state code, let's say you're in a state that hasn't adopted the 2009 IRC, so there are no state-specific makeup air recommendations, this tool is configured to go ahead and recommend solutions that are in compliance with the 2009 IRC. And again, these outputs of the tool will vary based on the acceptable design depressurization limit, which the IRC does not stipulate. So it's kind of a cross, or a meeting of design objectives, engineering objectives with minimum code compliance requirements. So something to consider there. Let's see, is there a formula to determine what the exhaust flow of the range hood should be? I think you can get away with 200 CFM flow hood rate often, not needing 300 or above. And there are equations out there, recommendations that are provided by HBI that can be used to find recommended range hood sizes. There are also recommendations provided by manufacturers that can be followed. And yes, you don't always need a 300 or greater CFM range hood. Sometimes you have very custom homes and solutions that have very large, do need a very large flow. And there's been a lot of research recently on kitchen pollutants and suggestions for sizing range hoods to be larger than traditionally sized, to ensure that cooks are exposed to less range hood pollutants, or less range pollutants during the act of cooking. A lot of work out of LBNL right now on that subject matter. So as we're learning more about kitchen pollutants, sizing slightly larger is not a bad idea. Another question here from Mark. Do you ever filter makeup air with carbon on high efficiency filtration to reduce O3 and PM 2.5 intake? So basically ozone and PM 2.5. Filtration is an option for makeup air or for any outdoor air that's being brought into the house. That's certainly something that the designer can pursue. It's not required right now within codes or standards, for that matter, unless there are certain standards that require it in case of conditioning that air being brought in through heating and cooling systems. But in this case, there are no standardized requirements for that or code requirements. So this tool has not addressed that at this point. But Mark brings up good considerations for those people who are interested in improving the indoor air quality of the outdoor air that's being introduced. Let's see, a question here from Armin. Compared to the real-world difference between metal or flex duct resistance, the differences in end cap resistance is many times more important. So Armin does bring up a good point that that the end cap is something that can really have an impact on the design. And so when you're selecting an end cap, it's important to look for one that that has a low depressurization trigger, or opens at or has low resistance, I should say, to flow. And unfortunately, that information is not widely available right now from a lot of manufacturers. So we didn't want to complicate the tool with inputs that designers might just not have access to. Down the road, as that information becomes more widely available, it's a great suggestion for an improvement to the tool. Let's see, a question from Paul here. The approach of allowing outdoor air into the HVAC system is a disadvantage because of a large influx of outdoor moisture. All that being said, what is wrong with ducting the outdoor air intake near the exhaust hood to reduce the risk of elevated indoor relative humidity? Nothing at all, Paul. If you are able to introduce the outdoor air near the range hood, you're right that you're going to be providing air that, that if it is humid, can more easily be exhausted, I guess, before it has a chance to mix fully with the indoor environment. So if you're in a very high humidity area, then that might be a consideration. And again, based on Debbie's comment earlier, another way to deal with it would be to actively dehumidify that air as well. So it looks like we're almost out of time. I think that's all the questions we're going to be able to address today. But I wanted to point out again that if you do need BPI or AIA credits, then please do send an email to Sam Bowles at the address here, and we will work to get those for you. And again, if your question wasn't answered today, we'll do our best to get back with you shortly. So thanks again for joining the webinar, and we'll look forward to touching base the next time.